All these scenes have one thing in common. Some object, large or small, moves through a gas or a liquid. In each case, the object experiences a resistance to its motion through the fluid. This resisting force is called drag. Unless some other force is applied to overcome the drag, the object will decelerate. Fluid dynamics is concerned with gases and liquids in motion, in particular with the forces applied to objects by liquids and gases in motion, and conversely with the way in which these fluids move under the action of forces applied by objects. Before Galileo performed his famous experiments at the Leaning Tower of Pisa, it was thought that a feather falls more slowly than a steel ball because it weighs less. Now we know that the feather falls more slowly because, as compared with their weights, the air resistance for the feather is much greater than for the steel ball. We can prove this by allowing the feather and the ball to fall simultaneously in this tube from which the air has been evacuated. Here at the top of the tube, ready to drop, are a steel ball and a feather arranged to be held up by a strong magnet. There, the feather did fall just as quickly as the steel ball. As a matter of fact, the speed of fall in a vacuum is the same for all bodies, regardless of their size, or their shape, or their material, or their weight. When we removed the air resistance, both the feather and the ball fell freely with the acceleration of gravity. If only the Greeks had been able to perform this experiment, the principles of mechanics might have been discovered 1,500 years earlier. What the Greeks thought, you remember, was that to keep a body in motion with a constant velocity, it is necessary to push on it continuously with a force, while Newton taught us that if a body is to move with constant velocity, the net force acting on it must be zero. The Greeks made their experiments on flying stones, arrows, and the like, but they did not understand that the air, although invisible and impalpable, exerts a resisting force which slows the object unless some additional external force is applied to overcome the drag. Over the past century, tremendous strides have been made in our understanding of the fluid mechanics of drag. Now I would like to show you, in the laboratory containing our demonstration wind tunnel, some curious phenomena relating to drag. We have here a small open-jet wind tunnel. The air escapes from the settling chamber through this nozzle at speeds up to about 230 miles per hour and may be controlled. You can see that this jet is something we can really work with. For instance, we can suspend models in the jet at this end of the lever arm system. The lever arm is mounted in ball bearings which act as a fulcrum point. The drag force exerted on the model by the airflow is transmitted through the lever arm to this spring weighing scale on which we may measure the force. These weights are counterbalance weights which we can mount to counterbalance the weight of the model so that the scale will read zero when there is no airflow. The can here contains a viscous oil to damp out oscillations in the pointer reading which arise due to any instabilities in the airflow. During the experiments, we would like to measure the airspeed as well as the drag. The airspeed is determined by the pressure in the settling chamber from which the air is supplied to the nozzle. The pressure is led by this tube to the pressure measuring instrument. The liquid level in the tube gives us the airspeed directly in miles per hour. Now I would like to begin with a few experiments with a specific object in mind. That is, I would like you to realize from the outset that sometimes what happens in a fluid flow is not what we may expect. This will suggest to us that many phenomena in fluid mechanics are very complicated indeed, and it will caution us to be on guard against reaching oversimple conclusions. In the first experiment, I suspend a 3-inch sphere at the end of the lever arm in the air jet. We are going to increase the airspeed and see what happens to the drag force. I'm going to start the motor now. Here we go. You see that we have brought the speed up to about 75 miles per hour, while the drag force reads about 1.5 units on the scale. I'm now going to increase the wind speed to about 100 miles per hour. The wind speed, you see, is about 100 miles per hour, while the drag force has increased to something a little less than 2.5 units. Now I am going to increase the wind speed continuously, and I'd like you to observe what happens to the force on the scale. Here we go. Up, 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 but now it's going down, down, and up again, up, up. She's continuing to rise, continuing to rise. Now that was very puzzling, and it's not quite clear what happened, so I think we'd better repeat it. I'm going to reduce the speed to about 75 miles per hour again, so that we can do this all over again and make sure that we saw exactly what happened. There we are, back at about 75 miles per hour again. Now I'll remind you that the puzzling thing that happened occurred when the force on the scale reached about 3 units and then suddenly dropped back to a little less than 2.5 units, after which it began to rise again. All this while the speed continuously increasing. I'll keep this button pushed all the time so that the speed continuously increases. Here we go. Up, up on the force scale, up, 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 down, 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 up again, up, 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 up. And now as she increases much more slowly in this second pattern of flow than in the first pattern of flow. Well, this is certainly unexpected. So as to make sure that we really understand what has happened, let us put our observations on the board in the form of a graph. On the vertical scale, we record the drag force. On the horizontal scale, the wind speed. As we increase the speed from 0, the drag force also increased, just as it does when you put your hand out of an accelerating automobile. But when the speed reached a certain value, we found that a further increase of speed caused the drag to decrease, but in a rather disorderly and oscillatory way, until we finally reached a speed at which the drag force once again increased as the speed increased, but on a different curve. We have 2 curves here in which the increase of drag with speed is quite orderly. And so there seem to be 2 distinct patterns of flow with a sudden jump or transition between the 2, which occurs in some range of speeds. For our second experiment, the wind tunnel has been arranged with 2 identical nozzles discharging air from the settling chamber to the atmosphere. In this way, we get 2 air jets of the same diameter and with exactly the same airspeed. Our purpose now is not to measure the drag itself, but only to compare the drags of 2 objects at exactly the same airspeed. The 2 objects are mounted on the equal arm balance. We may then see which has the greater drag and which the lesser drag merely by observing the deflection of the balance. In this experiment, we are going to mount on the balance arm two balls of exactly the same diameter. From a distance, they look nearly alike, but they differ in a small yet all-important detail. One of them is very, very smooth. The other has on it some scratches, very fine scratches, together with this narrow strip of thin plastic tape. Observing these very slight differences in surface geometry, you would hardly expect that this could make very much difference to the airflow or to the drag. I'm now adjusting this pendulum weight so that the lever arm will be horizontal when there is no airflow. We're ready to begin the experiment now with a roughened ball near me and the smooth ball on the far side. You see that the speed begins at 30 miles per hour, and the deflection of the balance beam indicates that the smooth ball has less drag, as you might possibly expect. Now I'm going to increase the speed, and as I do, the beam deflects still further, but the smooth ball has less drag all the time as the speed goes up to 75 miles per hour, 100 miles per hour, approaching 125, but there she turns over, and now you see that the smooth ball has more drag, indicating some sort of reversal in the flow pattern. This is very puzzling, and I'd like to do the experiment once more, so I'm going to reduce the airspeed. Now the speed is down again to about 60 miles per hour. I'm going to increase the airspeed steadily up to about 150 miles per hour while you watch the balance beam to see which ball has the more drag. Well, we would hardly have predicted that, would we? As a matter of fact, not only is the drag of the rough ball sometimes less than that of the smooth ball, but if we had made measurements of the drags of the two balls using the weighing scale, we would have found that at some speeds, the drag of the rough ball is only 1/5 the drag of the smooth ball. This certainly seems like a great deal when we consider how little different the two balls are. Surely we will have to turn to some fundamental ideas in fluid mechanics in order to understand why this is so, how such a very small cause as a slight roughening can produce such a very large effect as a 5-fold reduction in drag. Next we are going to do two related experiments, one in air, which has only a small viscosity, and one in glycerin, which has a very large viscosity. We begin with the air experiment. The wind tunnel is still arranged with the two nozzles and with the equal arm balance. One of the two objects whose drags we are going to compare is the smooth ball that we have just tested. The other is this streamlined shape. We might call it a bomb. Later we shall discuss more precisely just what we mean when we say streamlined. For the moment, the important point is that the maximum diameter of the bomb is precisely the same as the diameter of the ball. The difference between the two is that the shape of the bomb is more or less like a teardrop. There, we're ready now. We brought the speed up to about 30 miles per hour, and you see that there's a slight deflection of the balance arm, indicating that the bomb has slightly less drag at this speed. Now we increase the speed. We've gone up to about 50 miles per hour. You see that the difference in drag is even greater. Here we are at 75 miles per hour, 100 miles per hour. The bomb still has less drag. 125 miles per hour, 150 miles per hour. And as a matter of fact, we could have gone up in speed as high as we liked, and still the bomb would have had less drag. For the second of our pair of related experiments, we use these two tubes containing the same viscous liquid, glycerin. I am going to drop two models simultaneously, one in each tube, to see which goes faster. Here are the two models. You see that they are small-scale replicas of the models used in the wind tunnel experiments. One of them is a smooth spherical ball. The other is a bomb shape having exactly the same maximum diameter as the ball. In the wind tunnel, the two models were mounted on an equal arm balance in such a way that they had the same net weight in air, the fluid in which their drags were being compared. These models also have the same net weight, not in air, but in glycerin, the liquid in which they are to move. In the wind tunnel experiments, we compared the drags of the two bodies at the same speed. In the liquid, however, we shall compare the speeds of the two objects when each has exactly the same drag. Now, when we drop an object like this steel ball into a liquid, it at first accelerates. But as it moves faster, the drag on it increases until after some time it moves at virtually constant speed. This ultimate speed is called the terminal speed. Here is a stroboscopic photograph we made a short while ago. The time interval between exposures is constant, and so the distance between successive positions is a measure of the speed at successive instants. You see that there is a zone of acceleration which gradually merges into a range of constant speed. Now, and this is important, when an object moves uniformly at terminal speed, the sum of the forces acting on it must be exactly zero. At terminal speed, therefore, the drag acting on the object must exactly counterbalance and be precisely equal to the net weight. You see that the two models do have exactly the same net weight in glycerin. And so they have exactly the same drag when each moves at its own terminal speed. If the terminal speed of one is greater than that of the other, it offers less resistance to the flow. Now let us recall that in the wind tunnel experiment, the streamlined body offered less resistance to the airflow. At the same speed, it had less drag. The question now is, will it also offer less resistance to this viscous liquid? For the same drag, will it have more speed? They're already at terminal speed. Since these are plastic models, they drop much more slowly than the steel ball we dropped a moment ago. The answer to our question is no. For the same drag, the streamlined body has less speed. Conversely, if we were to make experiments at the same speed, we would find that the streamlined body has more drag. This result is just opposite to what we found in the case of the airflow. And once again, matters look complicated. Let us review now the several experiments you have seen. In one experiment, we found that sometimes an increase of speed actually produces a decrease of drag. In a second experiment, we found that in one range of speed, a smooth ball has less drag, while in another range of speed, a roughened ball has less drag. In the third experiment, we found that under certain conditions, streamlining reduces the drag, while at other times, Streamlining increases drag. All these results are either paradoxical or against our intuition. Obviously, a good deal of unraveling lies ahead of us if we are to put some sort of system and order into our understanding of fluid flow.